Good morning, everyone. Thank you so much for joining me for this webinar. So today I'll be talking about the revolving door of stinky sulfurs, and in this webinar I'll be discussing the formation of reductive aromas and how commonly used wine additives such as copper and SO2 and also oxygen can affect the evolution of these compounds post-bottling. So what exactly are these smells? So when we talk about reductive aromas, we refer to a group of volatile sulfur compounds that are associated with very bad aromas. And there are many sulfur compounds present in the wine, but only a few of them are rated as reductive aromas, and the ones that I've highlighted here for you are usually associated with these reductive aromas. And they are hydrogen sulfide, methanethyl, ethanethyl, and dimethyl sulfide. So these compounds are usually present in wine in very low concentrations, and I've highlighted their aroma thresholds here for you at the bottom. And it's only when they exceed these aroma thresholds that they become problematic. And then they're associated with aromas such as rotten egg and sewage for hydrogen sulfide, rotten cabbage and putrefaction for methanethyl, and onion and rubbery and a burnt match aroma for ethanethyl. So dimethyl sulfide is a pretty interesting compound. There we go, sorry. So dimethyl sulfide is a pretty interesting compound because when it's present in very low concentrations, it can actually enhance your fruity bouquet, and it's actually a positive attribute to your wine aroma. It's only when it's present in very high concentrations that it imparts aromas of truffle, cooked vegetables, and canned corn. And similarly with hydrogen sulfide, it can also actually enhance your bouquet when it's present in low concentrations, but it becomes problematic when it's in high concentrations. So as you can see, the aroma threshold is very low for hydrogen sulfide up to ethanethyl and methanethyl to 1.1 to 3.1 micrograms per liter. And even though in comparison dimethyl sulfide is higher at 25 micrograms per liter, it is still a very low concentration in ppb levels. And how do we get rid of these smells once they're formed in the wine? Well, the most common treatment used in the winery is copper fining, and it's very effective in reducing the impact of the unwanted sulfur compounds, and it also has a very long history of use in the beverage production industry. It has been used for centuries in the wine industry, not always necessarily by adding copper sulfate to the wine, but also through the use of copper equipment and copper vessels. And it's also been used in the beer industry for many, many years. So the beer industry doesn't really like to admit to this, but they also use copper rods and copper staves, and that reduces the impact of the unwanted sulfur compounds. And of course in the spirit industry, where the use of that enormous copper distilling equipment also reduces the impact of the unwanted sulfurs. And it's not by coincidence that copper is so widely used. It can be very effective in reducing the unwanted thiols. So let's have a look at some of the mechanisms of the copper's reaction with the sulfur compounds. So if we look at hydrogen sulfide is a very reactive nucleophile, and it actually reacts very fast with copper to form an insoluble copper sulfide complex. And when we have this in our wine, it drops out and our impact is removed. Mercaptans such as methanethyl and ethanethyl also react very readily with copper, and they also form insoluble copper mercaptan complexes, but this reaction is much slower than the hydrogen sulfide, and for a compound such as methanethyl, this can take up to 2 months to stabilize. If you have disulfides and trisulfides in your wine, such as dimethyl disulfide or diethyl disulfide, it can't directly react with your copper because it doesn't have that free sulfur moiety that we had previously with the hydrogen sulfide or the methanethyl. So you first need to reduce your disulfide to its corresponding mercaptan, and then it can react with your copper and be reduced. So if you have other compounds like dimethyl sulfide or your thioacetates like methyl thioacetates or ethyl thioacetates that can't react with your copper treatments at all, and if your wine is reductive due to these compounds, copper fining won't be effective. But at the AWRI, we get quite a lot of questions where they ask us, why does our wine go stinky again after it has been treated in tank? And also, why don't the bench trials always reflect what we see in tank? Well, the answer to this is that it's all a question of equilibrium. And even then, it's not as simple as we might think. Because when we consider our molecules, our sulfur molecules in the wine, it's very tempting to think of hydrogen sulfide and methanethyl as these free molecules floating around in the wine. But in reality, like we discussed previously, they're very reactive compounds, and they can react with a wide range of wine compounds, including other thiols and metals and proteins and polyphenols. And through these reactions, the chemical form of your thiols will change, and that will not only change their aroma, so you can go from your sewage type aroma to a meaty-like aroma or sulfury aroma, or to a spicy meat-like aroma, but this will also change your aroma impact of the wine. So, but this is a very complicated mechanism, so let's have a look at some of the simpler reactions that the sulfur nucleophides can be involved in. So if we start with hydrogen sulfide, it's got an aroma threshold of about 1.1 micrograms per liter. And I represent it here with this big nose to just show that it's got a large impact on the aroma of the wine, because, even if it's present in very low concentrations. But because it's such a reactive compound, it can interact with a wide range of wine compounds, such as methanol and acetaldehyde, and then it can form methanethyl or mercaptan. As you can see, the aroma threshold is very similar between hydrogen sulfide and methanethyl. So although your aroma is changing from a sewagey aroma to a more of a putrefaction and sewage aroma, it'll still have a very large impact on your wine. But this is also a very reactive nucleophile, and it can be oxidized to larger molecular weight sulfur compounds. So this will be our disulfides and our trisulfides. And although we're changing the chemical form of the methanethyl, it can still have a big impact on wine aroma, although the aroma threshold will be much higher now at 10 micrograms per liter. So these oxidized compounds, unfortunately, is not stable, and they can also be reduced back to methanethyl. This is not a one-way reaction. It can be reduced back, and then depending on our wine conditions, we can once again have a problem with methanethyl later on. And then methanethyl can also react through acetylation reactions to form our thioacetates. And if this happens, our aroma threshold will increase to 50 micrograms per liter. So the impact of the compound will be much less on the wine aroma. But once again, this isn't a stable compound, and it can be hydrolyzed back, especially in wine pH. And then we can once again have the problem with methanethyl at this low aroma threshold. So this scheme is a very simplified representation of just some of the sulfur chemistry that can take place in wine, but it's a very good way to illustrate and to show how the sulfide compounds in the wine is reacting and how they're not stable and how they can be involved in many reactions in the wine. So now it's time for some myth busting. So when we treat our wine with copper and to reduce our reductive aromas, we assume that all the copper sulfide complexes drops out as insoluble complexes. So this is what we think we're doing. If all our sulfur compounds are represented by this yellow sulfur dust here on the left-hand side, and all the copper we're adding to our wine is represented by our blue copper sulfide crystals, then we think we're adding a one-to-one copper sulfide to our sulfide complexes. But it's very important to remember that the amounts of sulfur compounds present in our wine, specifically the volatile sulfur compounds, are present in microgram per liter concentrations, whereas we're adding our copper sulfide in milligrams per liter concentrations. So in reality, the picture looks a little bit more like this, that we're adding a lot more copper sulfide complexes to react with a small concentration of sulfide compounds, and thus we're ending up with the increased residual copper in our wine. And it is not unusual to see that our copper values actually increase at the same rate as our copper additions in the winery. And what is the downsides of residual copper? Well, there's quite a lot. We all know that if we have residual copper in our wine, and specifically our white wines, that can lead to increased haze formation and protein instability. And also, our copper doesn't specifically only react with our reductive aromas. It can also react with our highly valued varietal thiols, such as 3-mercaptohexanol and 3-mercaptohexyl acetate. And these compounds impart our positive varietal aromas of passion fruit and grapefruit, and they're highly sought after by many consumers. And the addition or the presence of residual copper in our wine can also lead to a more rapid loss of SO2, and this also has a very detrimental effect on our wine, not only due to browning of the wine, but also an increased risk of oxidation and a decrease in or a shortening of the wine's shelf life. And then, of course, the area that I'm most interested in, the increase in volatile sulfur aromas. So I'm going to discuss with you a series of experiments that we did at the AWRI, where we specifically focused on the effect of different copper concentrations in different wines, and just to see what the effect was of copper and also some other additives like SO2 as well as oxygen on wine aroma. So in this first experiment, we sourced wine that wasn't previously treated with copper, a Chardonnay and a Shiraz wine, and then we increased our copper concentration to quite a dramatic and quite a high concentration of 3 micrograms per liter. But we were specifically interested in the ability of copper to catalyze the formation of hydrogen sulfide and methane thiol, and what effect the oxygen concentrations in the wine would have on the copper effect. So initially when we started our experiment, the dissolved oxygen was 1.1 milligram per liter in our samples, and then through the course of the experiment, this oxygen was consumed by the wine, so that after 4 months of storage, we had 0 ppbs of oxygen left in our wine. So let's first have a look at our Chardonnay samples. So right here we have, on our left-hand side, we have the hydrogen sulfide measured in our Chardonnay wines, and we have our methane thiol measured in our Chardonnay wines. And our control samples are shown in blue, and our copper-treated samples are shown by this red trace over here. And the aroma threshold for hydrogen sulfide is shown by this dashed line at 1.1 micrograms per liter for hydrogen sulfide and 1.8 micrograms per liter for methane thiol. So this experiment ran over 12 months, and as you can see right at the beginning, where I previously told you about the high oxygen concentrations we had in our samples. So when we added our copper, we immediately saw the decrease due to the copper concentration. And this is what we expect, that when we add our copper to the wine, it binds to our hydrogen sulfide and we reduce our hydrogen sulfide concentrations. But then slowly, over the course of the experiment, as the wine consumed the oxygen, you can see that the amount of hydrogen formed is changing quite a lot. So that reduced hydrogen sulfide didn't stay stable at a low concentration. It was actually increasing again over the course of the experiment. For the methane thiol, we didn't see that dramatic decrease initially, even at the high oxygen concentrations. But previously I mentioned that methane thiol is actually a little bit less reactive than hydrogen sulfide, and its reaction with copper takes a bit longer to stabilize. So after about 1 month, we can see there is a big decrease in methane thiol concentration. But then once again, as the oxygen was consumed in the wine, the methane thiol isn't decreasing, but it's actually increasing. But this copper effect wasn't so dramatic in the Chardonnay samples. So let's have a look at what happened in the Shiraz samples. So once again, we have our hydrogen sulfide measured in the Shiraz samples on the left, and our methane thiol measured in our Shiraz samples on our right. And we have our control samples shown by the blue trace, and the samples treated with copper shown in the red trace, and the aroma threshold shown by the dashed line in both the graphs. So for the hydrogen sulfide, once again, we see at day 1, when we measured its concentration, when the oxygen concentrations was very high in the wine, we saw that a big decrease in hydrogen sulfide concentration. But then, as the oxygen was consumed by the wine, we can see that a big change has taken place, and our copper is actually catalyzing the formation of a lot of hydrogen sulfide, up to twice the concentration of our control samples. For the methane thiol, we saw that in the beginning there was no methane thiol present in either the control samples or the copper-treated samples. But then after a period of storage, we can see when the oxygen was consumed at about 4 months, we can see that the methane thiol is increasing quite dramatically, much higher than the methane thiol was in the control samples. This is about an 8 time 8-time increase in the concentration. So it is pretty clear that not only is copper having a big effect on the evolution of hydrogen sulfide and methanethiol in the wine, but that the oxygen in the wine is also modulating the effect. So what we saw was that when we had lots of oxygen present in our wines, we saw the decrease in thiol concentrations as we expect. But as soon as the oxygen was consumed by the wine and after a period of storage, we saw a dramatic increase in hydrogen sulfide and methanethiol, and specifically in the Shiraz samples. So then we designed a second experiment, and in this experiment we were interested to look at a more industry-relevant concentration of copper, because as you remember, the previous one was pretty high at 3 milligrams per liter. So in this experiment we sourced also a different white wine, a dry white wine blend, and a Shiraz wine, and then we the base wine had 0 copper added to it, and then we spiked it to a higher level of 0.5 micrograms per liter. And this is the European Union limit for export for Australian wines for copper concentrations. So in this experiment, everything was treated anaerobically from the start of the experiment. And so because we didn't want to see the impact of oxygen again on our experiment, and we measured our hydrogen sulfide and our methanethiol concentrations. So this experiment is still in its early days. We've only measured 3 months of, we've only got 3 months of data, but already we can see the impact of copper on these wines. So if we look at our white blends, where we look at our hydrogen sulfide evolution and our methanethiol evolution, we can once again see our control samples in blue and our copper-treated samples shown in red. And here we can see that from the start we saw much higher concentration of hydrogen sulfide present in the samples treated with copper than in the samples without. So even though it is decreasing together, by adding copper to the wines, we have increased the amount of hydrogen sulfide present in those samples. For the methanethiol, for the first month of our storage, we didn't see any significant differences between the copper-treated samples and the control samples. But here, after 3 months, things are starting to look a little bit different. It seems that this trajectory for the evolution of methanethiol is changing a little bit. So it'll be interesting to see at our next time point in a few months where this methanethiol is going. And once again, for the Shiraz samples, we had a quite dramatic effect of copper in the wine. So when we added the copper to the wines, we saw a slight decrease in hydrogen sulfide concentration, but that hydrogen sulfide increased quite dramatically after 1 month and then plateaued off a little bit, whereas in the control samples we saw a steady decrease in hydrogen sulfide concentrations. And if we look at the methanethiol concentrations, we can clearly see that as for the white blend, initially there wasn't a significant difference between the control samples and the copper-treated samples. But then after about 3 months of storage, we can see that the way that the methanethiol is evolving in these wines are changing quite dramatically. And this is the thing that we should always think about when we're adding copper to our wines, that we are changing the way that the hydrogen sulfide and the methanethiol is developing post-bottling. So by adding the copper and just assuming that it'll decrease your thiol concentrations doesn't necessarily mean that that'll be your end result. You might end up with a big increase in your hydrogen sulfide and methanethiol concentrations. So in a third experiment, after we saw a very big increase at a high concentration of copper and a slightly less increase at a lower concentration, we designed an experiment where we looked at different copper concentrations and in a Chardonnay wine, and we also looked at it in a fined and an unfined wine. So we added our copper at 0 milligrams per liter, at 0.2 milligrams per liter, at 0.5 milligrams per liter, 0.75 and 1.5 milligrams per liter. And once again, we were interested in the copper's effect on the formation of hydrogen sulfide and methanethiol. And the reason we looked at the fined and the unfined wines was that we know that unfined wines with a higher protein concentration might potentially have extra precursors to these sulfur compounds because they contain quite a lot of sulfur bonds in their protein structure. So let's have a look at the results of the Chardonnay wine. So after 2 months of storage, we could already see that the copper was having quite a big impact on hydrogen sulfide and methane thiol. So in this graph we have, or in both graphs, we have our unfined wine shown in the blue bars and our fined wine shown in the red bars. And after 2 months of storage, there's not a big difference between the fined and the unfined wines. But what we can see is that the increase in copper concentration is leading to a stepwise increase in hydrogen sulfide concentration. And for the methane thiol, we can see a bit of a different parabolic effect of the copper. So initially we see a bit of a decrease in the methane thiol, and then but at very higher concentrations of copper we're seeing a dramatic increase in methane thiol concentration. And this is pretty dramatic considering our aroma threshold is about there, about there, 1.8 micrograms per liter. So this is nearly or 3 times increase in its concentration. But then after 6 months of storage, we can see that the hydrogen sulfide concentrations have plateaued off a little bit. So at the standard copper levels, they seem to have maxed out. But now we start to see quite big differences between our different wine samples and our wine's composition. So our unfined wines, after 6 months of storage, has got a significantly larger concentration of hydrogen sulfide than the samples without that has been fined. And for the methane thiol, we can see that it has decreased over the course of the experiment after 6 months of storage. And even though it's decreased here at the higher concentrations of copper, it is still a bit worrying because we know that the copper can catalyze oxidation reactions. So it is possible that the methane thiol has actually just been oxidized to a higher molecular weight sulfur compound and could be reduced back depending on our wine conditions. So this experiment just illustrates how important it is, or how important the wine composition is, and how that influences the role that the copper plays in your wine. So in a fourth experiment, we decided to not only look at copper, but also to look at another commonly used wine additive, sulfur dioxide, and to see how these two compounds interact in the wine in the formation of hydrogen sulfide. So for this experiment, we specifically sourced a white wine and a red wine, so a Verdelho and a Shiraz, that weren't previously treated with either copper or SO2. And then we increased the copper concentration to 0.5 milligrams per liter of copper, and we also increased the total SO2 for the Verdelho wines to 100 micrograms per liter. So let's have a look at the copper effect. So here we have our copper effect on the Verdelho wines in terms of hydrogen sulfide formation, and we have the SO2 effect on hydrogen sulfide formation also in the Verdelho wines. So here you can clearly see that, okay, so we've got our control samples here in blue, and our copper-treated samples are shown in red. And once again, this experiment was conducted over the course of 12 months. And here you can clearly see that if we treated our wines with copper, we saw quite a dramatic increase in hydrogen sulfide concentration of about 10 micrograms per liter after 6 months of storage. So that decreased again at the end of the experiment, but still there was quite a big increase in hydrogen sulfide. But our SO2 didn't really have any impact on hydrogen sulfide formation. It had a very variable effect over the course of the experiment. But the most interesting thing, or the most interesting aspect of the study, was when we actually combined the copper and the SO2 in the Verdelho samples. So when we treated our samples with a combination of copper and SO2, and we measured our hydrogen sulfide, we saw dramatic increases in the hydrogen sulfide concentration. So in this graph, we have our control samples shown here in blue, and our copper-treated samples shown here in green. And then we have our SO2-treated samples shown in purple, and then the combined treatment of copper and SO2 shown in red. So here you can clearly see that when we treated the samples with this combination of copper and SO2, we got significantly increased hydrogen sulfide concentrations. At the end of the experiment, we had a 40 times increase that of our control samples, and that is also a 40 times increase of our aroma threshold. So these wines were enormously stinky. And it's also important to see that even this combination of copper and SO2 had a 4 times higher concentration of hydrogen sulfide than samples treated just with copper. So there's definitely an interaction happening between the copper and SO2 that can lead to an enormous increase in hydrogen sulfide. But how is this happening? What is the driving forces behind this formation of hydrogen sulfide? So I'll discuss some possible mechanisms here with you. So if we look at the formation of hydrogen sulfide from copper and SO2's role, then we can assume that, or as we saw previously, we can see that the copper is catalyzing the formation of hydrogen sulfide from unknown precursor molecules. And then our SO2 can either have an indirect role or a direct role in the formation of hydrogen sulfide. So let's first look at the indirect role. So once we have formed our hydrogen sulfide through our copper catalyzed reactions, then we can have many other reactions that take place in the wine. So through reactions with some aldehydes, we can form benzaldehyde, furfuryl thiol, or ethane dithiol, and this will lead to the formation of higher molecular weight thiols, and this will quench our hydrogen sulfide by decreasing its concentration and increasing these concentrations. And the impact of hydrogen sulfide will be reduced on the wine. And then the hydrogen sulfide can also react with wine quinones. And this is a thiol quenching reaction. This is irreversible. So once the thiols have reacted with the quinones, we can't get them reduced back. And this will also lead to a decrease in hydrogen sulfide concentration. And then, of course, through the reaction with copper, we can also decrease the concentration of hydrogen sulfide. But if we have SO2 in the mix, then we can start to get competing reactions between hydrogen sulfide and SO2 with the aldehydes, and also competing reactions with hydrogen sulfide and SO2 and the quinones. So the SO2 also forms aldehyde adducts and quinone adducts, and they react quite readily. So a recent study has investigated the reaction rates between hydrogen sulfide and SO2 when competing for reactions with quinones, and they found that H2S and SO2 has the same first order rate constants, which means that the preferential binding of SO2 and hydrogen sulfide will be driven by a concentration of these compounds. And seeing that SO2 is present in micrograms per liter concentration and hydrogen sulfide is present in milligrams per liter concentration, it makes sense that the SO2 would preferentially bind to our quinones. So through competing reactions, the SO2 would quench the SO2 will quench the quinone, and that will lead to an increase in hydrogen sulfide concentration through an indirect mechanism. But other authors have also theorized that SO2 might be reduced through copper catalyzed reactions and in our wine to form hydrogen sulfide. So this pathway has only been proposed and has not been yet shown to be possible in real wine, but it's also something to consider. So another aspect of our study of experiment number 4 was where we looked at our Shiraz wines, and in these wines we were also looking for the effect of what the effect of copper and SO2, as well as the combined effect of copper and SO2 would have on the formation of hydrogen sulfide. So initially the concentrations of copper was 0 in the Shiraz wines as well as the SO2, and then we increased these concentrations to a 0.5 micrograms per liter of copper and a 60 micrograms per liter of SO2 in the Shiraz wines. So let's have a look at some of the results. So here we have our copper effect on hydrogen sulfide formation, our SO2 effect on hydrogen sulfide formation, and the combined effect of copper and SO2 on hydrogen sulfide formation. And our control sample is shown in blue, and the copper-treated sample is shown in red for all of these graphs. So as we can see, when we added our copper, nearly immediately after a month of storage, we could already see an increase in hydrogen sulfide formation due to copper catalyzed reactions. And at the end of the experiment, we ended up with about a 20 micrograms per liter increase above our control samples. But that's something we expect by now. Every time, and all the graphs I've shown you previously, if you add copper to a Shiraz sample, you always get an enormous increase in hydrogen sulfide. So we didn't see any effect of SO2 on the formation of hydrogen sulfide. And the combined effect of copper and SO2 was not as dramatic as we previously saw in the Verdelho samples. In this case, we get quite a different evolution pathway of our hydrogen sulfide, and the amounts of hydrogen sulfide formed is very similar to the copper effect. And when we performed statistical analysis, multi-way ANOVAs, we determined that this increase was not due to the interaction between copper and SO2 in the red wines, but it was solely driven just by copper. And this might be explained by a lower concentration of free SO2 that was available in the Shiraz wines compared to the Verdelho samples. But another interesting aspect, so like I said previously, copper treatment increases hydrogen sulfide quite dramatically. So the other interesting aspect that I want to show you is what we saw when we added some other wine compounds to this experiment. So we had our Shiraz wines, and this is the graph that I showed you previously, and here the blue trace is our control samples, and this green trace over here is the copper-treated samples. So we saw that big increase in hydrogen sulfide in our Shiraz wines, both for just copper treatment, and then also here at the bottom the green trace for the copper and SO2 treatment. But then we decided to add some cysteine as well as glutathione to these treatments, because we know that cysteine during fermentation can actually lead to an increase in hydrogen sulfide, and we thought that maybe cysteine and glutathione could also act as precursors for hydrogen sulfide through the desulfurization of their sulfur moieties over here, or maybe through the interaction of these sulfur moieties with other wine compounds. But interestingly, if you look here, you can see that the samples treated with copper and cysteine, shown in red, has produced a lot less hydrogen sulfide than the samples just with copper, and that the samples treated with copper and glutathione also produced a lot less hydrogen sulfide than the copper by itself. And similarly, we saw the same effects in the samples treated with copper and SO2. So when you treated your sample with a combination of copper, SO2, and cysteine, we saw a decrease, and then an even greater decrease if you treat your samples with copper, SO2, and glutathione. So why exactly is this happening? So we've got a possible mechanism that I can maybe walk you through. So if we have a hydrogen sulfide formed through copper catalyzed reactions from our unknown precursor molecules, or through the direct reduction of SO2 through copper catalyzed reactions, then we can have competing reactions in the wine, whereby your cysteine and your glutathione is actually competing to bind with your copper and preventing it from reacting with hydrogen sulfide. Because if you look at your, just go back a second, if you look at these molecules, you can see that a cysteine that has decreased the hydrogen sulfide concentration has only got a few functional groups that can actually bind to your copper. So that might explain why it's not completely removing the copper from the system, but only slightly reducing its effect. Whereas the glutathione has got a lot more functional groups that can bind to the copper, and that can actually completely encapsulate the copper and remove it from the wine and prevent it from binding any further. So my take-home messages for you today is, firstly, why do we have this difference between the wines? Well, we have to remember that there's no such thing as free copper in wine. It's always interacting in some way with a different wine species. As I've shown you previously, the copper, the SO2 and the glutathione and the cysteine and the oxygen can all interact and influence the way the copper reacts in your wine. So some of these compounds prevent the copper from being involved in the oxidation and reduction chemistry. So compounds such as cysteine and glutathione prevented it and actually reduced the impact of copper on hydrogen sulfide formation. But the other compounds such as SO2 actually led to an increase in hydrogen sulfide concentration. And it's important to remember that residual copper in your wine might change the formation pathways of your volatile thiols, and that your oxygen can also have a great impact on the amount of volatile thiols formed. So initially, when you have high oxygen present in your wine and you treat your wines with copper, the way that it interacts and reduces your copper or your volatile thiol concentration might completely change after a period of storage when that oxygen has been consumed in your wine. So it's incredibly important to tailor your copper additions to the wine in question and never to just make a standard addition. So when is it okay to use copper? Well, the best time is always to add it at the end of fermentation, because at that point you have the potential, you can eliminate the potential precursors as early as possible. And then there's also lots of wine solids and yeast solids that can remove as much of the excess copper as possible. And if you have to do copper fining later, it's important to know exactly what sulfur compounds you are treating. So it's important to do your bench trial first and to make sure that you are treating hydrogen sulfide, methane thiol, or some of your other mercaptans, and not trying to treat your thioacetates or your disulfides with copper treatment, because that won't be effective. And then also add the minimum amount of copper in the smallest aliquot that you can measure, for example 50 ppbs, that you don't accidentally increase your residual copper concentrations. And also give your wine time to stabilize before bottling. Some of these reactions take a lot longer to take place and to stabilize, so it's advised to give it up to 12 hours to stabilize. And remember to test your copper levels before and after addition, and never add your copper on the day of bottling. So I would just like to thank my team members, Eric Wilkes, Paul Smith, Martin Day and Mark Smith, and also the rest of the AWRI team for all their support and contributions to these projects. And also for AWRI, our funding body, who